Welcome to Dr. Jimmy's Applied Calculus. We're now going to start into Chapter 4 on whatever derivatives happen to be. Starting with looking at lines, which we've investigated with their slopes. And then try to look at that for general curves. So as an example, if we took a line y equal 2x minus 3. Okay, given an equation of a line, we could write the slope in this case because we see it as the coefficient of x. We also know that if we have 2 points, so for instance, if we had the point 1 minus 1, that's a point on this particular curve, and another point, 2 comma 1 is another point. And we could compute the slope as a change in y over a change in x. We've also written that as the difference in the y coordinates divided by the difference in the x coordinates. So from the 2 points, we get a difference in the y's over a difference in the x, and end up at the same value too. So different ways we've addressed lines and their slope. So this particular line has a slope 2, so we would see something in this upward direction. And we were looking at the slope, which is relative to finding change in y over change in x. Or we can use any right triangle. And so if we start at one point, then we move to another point. On the other hand, we could look at this as starting at a point, and then when we get to the other point, we've added on the changes. So different perspectives. Starting at this point, if I add the change in x and the change in y, I get to the other point. So this slope I could write as a difference between y1 plus the change and the y1 over the change in x. So for our particular example, we had a point 1 minus 1 that was on the line. We could take a change in x. Well, we could use maybe something like 0.5. So start at a point, take a small point, change in x. So what's y? if we start at 1 and add a half. So evaluating now at 2 times 1.5, and in that case we get 0. So we could compute change in y over the change in x. Now it's going to be divided by the change in x. Looking at it from this perspective of starting at the y value minus 1, I recomputed what happens if I add a half to the x and end up at 0. Again, it all comes out to 2, just a different perspective. Start at a point, add a change in x, which causes a change in y. Okay, so now for our example, if we look at this, we're going to start at a point x1, y1. We're going to add delta x, but I'm going to make a change here. Instead of calling it delta x, let's call it h. A little less cumbersome than the 2 symbols. So we'll use h instead. And so we'll end up at x1 plus h. And the next point y. But y2 we want to look at as what we would get if we evaluated y at the new value of x. So we're going to compute the slope, or one way we could look at that is divide by the change in x. I've rewritten that as h. Then we're going to compute y at the 1 value, and then go back to the equation and compute y again at the new value after we make the change of h. So all things we've done before with slopes are just a matter of perspective and a little bit of notation. Okay. That we're going to reference this to a point, make a change in x, which I'm now make a little simpler notation, call that h. And that will start y at a particular value of x and end up at another value, which would be what happens when x1 has h added. So now this line, the slope, we notice goes up, it goes down, does different things. In many cases, we could think of that as the direction of the line. So if you had a line on a map, it would be your direction, elevation of something up or down. So direction is another way to interpret slope, or you can interpret slope as a direction. So now, if we take a general curve described y as a function of x. It may not be a line. Some of the things we thought about with lines would still apply, such as if we're at a point, we can think, what's the direction at that time? So at each point on this curve, and look, what direction are you headed at that moment? So if you're walking along here, at this point, what way are you facing, which is off in this direction? That will change, though. If I take a different point and I keep walking, and I'm here, I have a different direction now, but I still have a direction. So I get over here, I'm direction in completely different direction than back here. So different from a straight line. Direction is always the same. General curves, we have directions, but it can change as we move. But there is a direction. Now, one word to refer to that direction is tangent. So there's a tangential direction at each point. So how do we move tangentially? So that's going to change and be different as we move along. So different directions move to different points. Now, relative to up and down, we probably say this is positive, and here it's negative. So sometimes, according to this path, we're going positive up or negative down. There are a few places somewhere about here that seem to be not up or down. So sort of a zero direction, non-changing. So we go up, we go down, sometimes we don't change, at least for an instant. So all the directions have the same flavor as following a line. It's just that as we move along the curve, the path, that direction changes. Okay. And so to get at that direction, we could call it the slope at the moment. So there's a tangential direction which would have a slope according to that tangential line. So we're going to take the slope that's constant for a line and come up with slope at points on curves, which would be changing. So if we took a piece of y equal f of x, and we wanted to somehow come up with a tangential slope, we could use approximations. So take 2 points on the curve, connect those points. We have a straight line between 2 points, and so up to a certain amount it approximates the curve. Now, such a line that crosses 2 points is a secant. So we could work out the secant slope if we wish. So we're going to start at a point. We're going to end up at another point, but we get here by changing the x, which gives us a new value, which is on the curve. So it would be the new x, x1 plus h, and then evaluate the point on the curve. So we go from one point on the curve x1 and some height, and add to h, which then forces us to another point on the curve. But now we're going to look at, well, what if we just went straight across? That would give us a particular slope. Okay. So in the picture, clearly not the same as the tangential slope. But what if I moved and picked a different point and did the same thing? The slope of that secant is much closer to the slope of my tangential direction. Of course, I could be more refined and take another point. Look at that line. Now my slope of my secant is very close to being the tangential direction. So the difference between the points is how far did I move. So this close point gave me a better approximation than moving far away. So it all depends on how big is h, how far did I move. So smaller h's, better approximation, larger h's, not as good. But we have a way of approximating what direction are we going to go. So we could look forward a little ways, compute what happens if we were going straight instead of actually following the curve. So, for example, let's take y equal f of x defined by 2 to the x. And use a point at least at 2. So what's the tangential direction or slope at 2? Well, we'll approximate. So let's get and look at some secant slope approximations. So that's just a matter of what is the change in x. What size of movement are we going to take? And that's the h. So let's look at a rather large h, maybe 1, something a little smaller, maybe 0.1, and then smaller yet, maybe 1/100th. As an example, we could do more, but we'll take those. And so this all depends on starting at 2 and moving by a value of h. So this will be f at 3 if h is 1, or f at 2.1 if h is 0.1. The functional value at 2.01 if we use 0.01 for h. So add h on each time. So we get 8 if it's 2 to the x, we get approximately 4.2871 if h is 0.1, approximately 4.0278 if we choose an h of 0.01. So we're going to look at the value there, 2 plus h, subtract the value we started at, all divided by h. First, the value of the function at 2 is 4. So we're going to subtract 4 and divide by 8. So we get 4, we get 2.71, and then we get 2.78 approximately. So, what direction, what's the tangential slope? Well, 4, that's probably a poor approximation. 2.871, a little better, 2.78. We could compute with even smaller h's and hope for even better approximations. So we have direction of the curve. We have at least ways to approximate that direction using slope, change in the functional value over the change in the x. Let's consider a general curve again, some y equal f of x. Here's a rough graph of that. So I'm going to look at if we're considering the slope of this curve, y equal f of x, or the direction at any particular point, we can consider when is the slope positive. So when can we draw a tangential direction that goes up? So we see some places up, but on this particular picture, some places down. But if we look at it carefully, there seems to be a point at which we quit going up and start going down. So a couple of those places. So it looks like if we stay less than -1, we have an upward slope, or approximately -1. And if we go from there to 2, approximately down and negative slope, and then back to positive. So for upward direction or positive slope, it seems anything less than -1 or anything bigger than 2. So approximately in my picture. So the -1, the 2, plus or minus a little bit maybe. Of course, we could have asked where is the slope negative. And that's the part between something close to -1 up to about 2. And then we could wonder, where is the slope 0? And that would be at those places we saw where it changes from positive to negative slope. And so there were a couple of places on this graph, somewhere close to -1. That the direction is pretty much horizontal, and also over at somewhere close to 2, we get a horizontal direction. And everywhere else it seems to either be a direction upward or a direction downward. So positive slope, if this is something like a profit curve, the profit is going up. If we have a negative slope that we're not gaining, we're losing, we have less and less profit. Although in the picture all the profit is above 0, so it's all positive, but in certain places we're gaining more profit. In other places we're not making as much profit. And then we have these points of 0 slope where momentarily we're not making more or less profit than before.